So anyway, this is the second installment of this year's Capsule Research Talks, which is for the purposes that postdocs kind of introduce themselves to the department. Again, the rules are just that everyone gives a 20-minute talk, which is pretty strictly enforced, and then you have time for questions. So today, it's my pleasure to introduce Rob Silversmith. He got his PhD at the University of Michigan with Robin Ryan, and now he comes to us as one of the Simon Center math postdocs. And he's going to speak about moduli spaces of curves and orbifolds.
Okay, thank you for the introduction. So I'm also speaking next week in the algebraic geometry seminar. So part of the end of this will hopefully be a little bit of an advertisement for that. Okay, so I want to start off with just a motivational question. Okay, so I want to consider twisted cubics. Okay, so by a twisted cubic, I mean a rational, smooth curve of degree 3. Huh? Oh, well, it's a copy of P1. Yes. Of degree 3 in complex projective 3 space. Okay, so this is like a very familiar object in algebraic geometry. It's often kind of the first example you see of a projective variety that's not a complete intersection. And there are, plenty of interesting enumerative questions you can ask about these, but here's one. How many of these things pass through 3 general points and intersect 6 general lines? Okay, so if you hand me 3 random points and 6 random lines in P3, how many twisted cubics hit all of them? And the answer will hopefully be a finite number. Yes, so I'll show that in a second. But I've cooked up the dimensions in the right way. Okay, so this question kind of comes with a natural approach. Namely, we want to consider a moduli space of twisted cubics. Okay, so in other words, we want to take a space of all of the twisted cubics, and passing through a particular point will cut out some subvariety of that space, and passing through a line will cut out some other subvariety. And you take all of these 9 subvarieties and you intersect them, and you hopefully get a finite number of points, and I want to know the size of that set. So it's all taking place inside of this ambient space. Yeah. Well, yeah, it's a good. I don't know where that terminology comes from. It's some historical, yeah.
Calculus. It's a term from calculus. Like 1 t squared t cubed.
They look kind of,
So it's a qualitative name.
Yes, definitely. Yeah, it's a non-degenerate curve.
Which is P1.
Right, and it's not contained in. I mean, it could be a plane curve, but it has
generic or possibly generic.
Something like that. In a plane. Yeah. Yeah, I don't know if people use the same, not planar. I don't know if people use the word twisted for any other higher generalization of this or not. Okay, so let's think about this moduli space in a couple of different ways. So the first way is that a twisted cubic has an ideal cutting it out, and that ideal is generated by three quadratic polynomials. Thank you. And it has Hilbert polynomial that you can calculate 3t plus 1. And so that says that a twisted cubic corresponds to a point in Hilb 3t plus 1 of P3. And the space of all twisted cubics will give you an open subset of this Hilbert scheme. Okay, so this is one way to kind of get a little bit of a handle on what this moduli space is. Another way is, well, this is a P1 embedded in P3, right? That's what a twisted cubic is. And so we can consider maps from P1 to P3, but we don't care about the coordinates on the twisted cubic. We just care about the image curve. So this is going to be up to PGL2. And if you try to write down such a map, what does it look like? ST maps to, well, I can write out long thing like this. Squared t plus so on. And there are 4 of these polynomials, each of which has 4 coefficients, for 16 coefficients altogether, except that if you scale them all simultaneously, it doesn't change the map. So we have a P15 of things that look like this, except that some of these maps will have base points, and some of these maps will be covers of their image, and some of these maps will be singular maps to a plane curve. And so we get some open set inside of this P15. And
what about the PGL2?
right, so this moduli space, the same one, is going to be isomorphic to U modulo PGL2. Okay, so that's another way that we can possibly get a handle on this M, by looking at some open subset that maybe we can kind of describe and taking a PGL2 action, taking the quotient. And this action is free. It's easy to see. Okay, so this last description, since this group is 3-dimensional, this shows that the space we're talking about is 12-dimensional. And that also shows that I cooked up this problem correctly, because passing through a point is a codimension 2 condition, and passing through a line is a codimension 1 condition. So you add them all up, and you get a codimension 12 condition on this space. Okay, any questions? Okay, so that's the setup. Both of these descriptions don't really give us much in terms of explicitness. Like, we can't write these things down very easily as, a nice quasi-projective variety. And so they're kind of a priori difficult to work with. And in particular, remember, we want to take intersections in this moduli space. And those are kind of difficult to work with if you don't know all that much about the variety.
So it's smooth?
It is smooth. In fact, it's homogeneous. All twisted cubics are just off by a projective change of coordinates. Okay, so since we don't know very much explicitly about this space, what can we do? We want to study these intersections topologically. So we want to know about the topological intersection theory of M. So what do I mean? I mean multiplying things in the cohomology ring and intersecting that way. But that doesn't really work very well for non-compact things. If I intersect something, if I intersect a bunch of subvarieties and I get a finite class of points, then that will be 0 in cohomology, since this is non-compact. So we need to compactify our space. Okay, and well, one compactification is already staring at us. The Hilbert scheme is compact, and M is an open subset of a component. It's actually not irreducible. But that's not the compactification I want to talk about. I want to instead start with the second way of looking at the moduli space. So, and I want to introduce a space called the space of stable maps. Okay, so a stable map is defined as follows. Let X be a smooth projective variety. So this is a much more general definition than we need for this example. And beta, a homology class of a curve in X. Then a stable map to X with some stuff fixed, so of genus G, degree beta, and I'm going to add an extra structure called markings with n marked points, is a nodal genus G curve C and a map from C to X, and it should be degree beta, meaning that if I push forward the fundamental class of C, then I get beta. And there's one more condition. Let's see, I did say n marked points, so this is actually a curve with n points remembered on it that I'm going to use later. And this map has to have no infinitesimal automorphisms. Okay, so this is a bunch to digest. So let me just write down a couple of examples. So first of all, this is supposed to be related to this twisted cubics problem. So if I have a twisted cubic C, then the inclusion from C to P3 is a stable map. And it's genus 0. I haven't remembered any points. Beta is 3 times the class of a line. And it has no infinitesimal automorphisms just because it's an inclusion, and that would mean an automorphism of C that commutes with the map. So that clearly can't happen except with the identity. Okay, and then here's kind of a schematic picture of what these things look like in more generality. You have a bunch of irreducible components, all connected in nodes. So this would be genus 3. And a map to X. And this condition that it has no infinitesimal automorphisms means what for this particular one? Well, the only constraint actually is that this component cannot be contracted to a single point. Because if it were, well, this component is a Riemann sphere with one special point on it. And so it has a 2-dimensional automorphism group that fixes this point. And if it were contracted to a single point in X, then all of those automorphisms would commute with the map and give you an automorphism of the map.
Sorry, can you say what? What do you mean by infinitesimal automorphism exactly?
I mean that, I mean an infinite. Okay, so first, an infinitesimal automorphism of the map means an infinitesimal automorphism of the curve that commutes with the map. And an infinitesimal automorphism of the curve means, well, yeah, so I mean, if the curve were high genus, then this would actually, I could also just say must have finitely many automorphisms. Maybe that's a nicer way of saying it.
So, but then maybe I don't understand for the twisted cubic, why can't you just
because that wouldn't commute with the map. Right? I mean, they would have the same image, but like if you take a point on the curve, then it gets sent to some other point by the automorphism, and then the map sends those 2 points on the curve to different points of P3. Yeah. Yeah, good question. Thank you. I was unclear there. Okay, so the point of this space, I called it a compactification before. So let me say what I mean. So this is a theorem from the 90s of Kontsevich, and then kind of maybe made completely rigorous by Fulton and Hunter-Epande, that says that the space, which I will denote like this, so this is the space of stable maps with these fixed invariants, is a proper separated Deligne-Mumford stack. Okay, so if you, nicer language here would be, or slightly different language would be a compact orbifold with singularities. So Deligne-Mumford stack just means a possibly singular scheme, locally a possibly singular scheme modulo a group action. Sorry, thank you. Yes, a finite group action. Yes, that's the important thing, so thank you. And furthermore, a nice special case, not a special case of this theorem, but a thing that's true about the special case where we're in genus 0, mapping to projective space. This is smooth and irreducible. So it's actually a smooth orbifold. It's kind of the nicest thing you can possibly hope for. And twisted cubics, this is fit in this category. In this case, yes. In general, not necessarily. In general, usually no. Because in general, it has lots of irreducible components of all different dimensions. Okay. So, what's that?
And the dimension can be bigger than the formula.
Yes, it certainly can. Yeah, just like in the case of the Hilbert scheme, in this example, where the other component of the Hilbert scheme had dimension 15 instead of 12.
What formula are we talking about here?
There exists a formula that Francois will tell us about in a few minutes for the dimension of this guy. Yeah. Yes.
Everything we can know is
Yeah, well, some version of that. If the only things in here were smooth curves that deform in the way you expect them to, then that would be the dimension. Okay, so I see that I'm almost out of time, so let me just take a second to think. Yes, so, okay, so an example of this, just to show that we recover more classical things, is if X is a point, then this space is nothing but the, so MGN bar, the Deligne-Mumford compactification of the space of marked Riemann surfaces. So something that, lots and lots of people can get excited about. Okay, so let me end by mentioning, so I won't get to do the advertisement for my talk next week, but let me end by mentioning a generalization of this that I promised in my abstract. So one might have reasons to want X to be not a smooth projective variety, but actually an orbifold. And I will give an example that will say one possible reason. And one can ask, does this thing still work? And the answer is yes. So in order to make it work, you need to change your notion of stable map. So these curves were just nodal Riemann surfaces. And you just change it slightly so that these surfaces are allowed to have, these curves are allowed to have orbifold points. Okay, and if you make that modification, then the space of stable maps from orbifold curves to a smooth orbifold satisfies the same statement. Okay. And so I'm going to talk a lot more about these spaces next week, but as a parting example of why one might care about them, let's take X to be an extremely trivial-looking orbifold. So take a point and mod out by the trivial action of a symmetric group. Then what is this space? It turns out to again be something previously interesting. Then the space of stable maps to this orbifold is a space of admissible covers. So these were introduced by Harris and Mumford in the 80s, and they're kind of a compactification of Hurwitz spaces, so spaces of covers of curves. And to make this completely precise, I should say, is the normalization of a space of admissible covers. Okay, so covering spaces of Riemann surfaces, yeah. Yeah, and so these have been, well studied for the past 30 years, and so it's again, interesting that they're cropping up as a special case of stable maps. And this is a result of Abramovich, Corti, and Vistoli, I should say. Okay, so I think I'll end there. Thank you.
Okay, any questions or comments?
Smooth orbifold mean? I mean, I know what orbifolds mean, but I already think of them being smooth.
Okay, yeah. So I mean, it's just
Based on a manifold. I mean,
it means an orbifold.
okay.
You can just.
Okay.
I mean, we often abuse language a little bit and refer to Deligne Mumford stacks as orbifold. Yeah,
Smooth.
it is. Yes, reassurance.
What's the answer to the question you started with?
192. And I was hoping to say a little bit about how one computes that, but I will move that to my. Well, no, it'll take quite a. It'll probably take 10 minutes, so I want to let Francois get to his talk.
How does your work fit into this?
Yeah. So, well, of course, the short answer is come to my talk next week. But so my work is about my thesis is about a particular orbifold, the symmetric products of projective spaces, or a particular class, and a particular class of orbifolds.
That one.
Yeah, this class of orbifolds, and what the challenges are that come up in computing their Gromov-Witten invariants, and in particular. Okay, and another class of varieties that's conjectured to be related, and yeah.
You have your cubed example, like twisted cubics for these spaces?
I don't. That's why I went with twisted cubics, because that's where the cute examples are.
Is it all D?
Mm-hmm. Yeah. Yeah, I think some low D was already done.
Okay. Okay, then let's thank Robert.